G'day, this is Mr. Thompson, and this video is for my Year 12 Physics and Engineering students who are about to go on a go-karting excursion later this week. So in class, we started to build this spreadsheet. We never quite got through it. We started to build this spreadsheet which will help us analyse the racing line around a corner. Now that's not a particularly good racing line, but the idea is to show you how to use it. So what I've done here is I've mapped out a racing line, and I'm thinking maybe this could be a little sneaky, try to get around the inside type racing line while all the other drivers are going wide. We might try to sneak around the inside. Now, is that a fast racing line or not? So the analysis of this spreadsheet is going to analyse this line segment by segment. You can see I've got 5 segments there. And for each segment, we're going to work out the velocity and the distance and the time and all that stuff. Some are more complicated than others, for example, the circular paths. Our total cornering performance for this particular racing line is to get from this dotted line here to this dotted line here would have taken, according to our calculations, 7.72 seconds. And what's just as important as the time is your exit speed. So if you've done some go-karting, you will know that it's one thing to get around the corner quickly, but if you get around the corner quickly and you're traveling slowly, then the person who's come around the corner and maybe taken a little bit longer to get around the corner, but they had a faster exit speed, is going to leave you in their dust on the straight, because they will have they'll be moving faster than you, and if you both accelerate at the same rate, because they exited the corner faster than you, they will be gradually but surely but steadily pulling ahead of you. The total time is important, but the exit speed is also important. So they're the 2 aspects we're going to analyse of a racing line. Now, we started with PowerPoint. So let me just quickly, there's PowerPoint. Let me show you how we get started. So we're going to place these segments on the PowerPoint there, and this is an actual photograph from Google Maps of the first hairpin after the straight at Kingston Park Raceway. So this is the track we're going to be racing on. So I guess let's lay these out a bit. So let's pick a more neutral sort of path. Let's go down the middle. Again, is this the fastest racing line? No, it's not. I want you to put the fastest racing line in. What do you think the fastest way to take the corner is going to be? So I want you to do a bit of experimenting. But let's do this one just so I can show you how the process works. So this first segment is just going full speed at top speed, not touching the brakes, just foot flat on the accelerator, assuming that we've already reached full speed coming down that stretch there, down the straight. Then at some point we're going to slam on the brakes, and we're going to slam on the brakes because we want to slow down so that we're ready to take this corner. Now, good practice is to slow down to your cornering speed before you start to corner. It's a bad idea unless you're a very expert racing driver and you know about trail braking and stuff like that. For us normal race drivers, weekenders, the best strategy is to slow down to the appropriate speed before we hit the corner. So now we don't know where to brake yet. We'll have to work that out. So I'm just lining those up. So somewhere between here and here, we need to transition from going full pelt here to hitting the brakes and slowing down. So we'll calculate that in a minute. So there's nothing in there, but we'll fill that up later. Now, the next section is to turn the corner. Now, I'm assuming that in our calculations, we've been doing circular motion in physics, haven't we? So we're going to assume this is a circle, not an ellipse, not a parabola, not some sort of exponential curve, because the maths for them is hard. And this is not a bad approximation, you know. So we're going to come around this corner. Now, I want to change the radius of this corner. Here's what you shouldn't do. If you grab one of these sides, see these handles here? If you grab one of those handles on a side and start to change it, can you see that's not circular anymore? So let's not do that. Control Z. If you want to change the radius of the corner of that path, grab one of the ends, one of the corners, one of the handles on the corners, and increase it like that. So there we go. So that's still circular. Let's move it here. Actually, that's bigger. I don't want to go that big. I'm thinking about, let's see, no, I can go tighter than that. I might do that, like that. That means I need to pull this back a little bit. Yeah. Here's another tip. To place your segments exactly, use the arrow keys on your computer. You'll get much more fine control like that. Okay, so I think that's what I'm going to do. There's my, so braking, corner at constant speed, and then I'm going to put my exit. Now, when you're exiting a corner, you don't want to stay at constant speed. You want to accelerate. So that's what this green section here is, exiting the corner, but trying to accelerate. And to accelerate, we're going to need to have a bigger radius. So let's open the radius up because we've got to, well, we'll talk about that in a minute. Okay, so there we go. Now, what I can't do, let me just show you this. If I try to do something like that, okay, I can't do that because see how that's got a really tight bend there? We've got this nice radius here, and then all of a sudden I'm asking my cart to turn really sharply there. I'll spin out if I do that. So we're not going to do that. Let me do Control Z. So all of these joins between the segments need to be tangential. So straight line here, that line's a tangent to that circle, and this radius here needs to be a tangent to this radius here. So let's make that tangential again like that. Okay, that's good. All right. Next thing I want to do is, and now actually, can you see it doesn't matter that the center of that circle there is not the center of that circle there. That's okay. That's fine as long as those edges, those shaded edges, as long as they line up and the two circles don't overlap. If the circles overlap, it means that we've got too tight a corner there. All right, now once we've exited that corner, actually let me just show you a trick. If I click on that segment again, see those orange, those yellow handles? I can decide how far I want to go around the corner. I'm going to go to about there, I think. That'll do. So a little bit more than 90 degrees. And then I'm going to put this last segment on here. And this last segment is the segment that accelerates out of the corner. Now I might have to tweak that. I might have to rotate it a little bit. Actually, that's pretty good, I think. Again, that's got to be tangential there. It's got to be a tangent. You can't do something like that. That's no good. You can't even really do something like, I don't know, you can't do something like, not that you would want to, you can't do something like that. You've got to come out at a tangent to the circle. Otherwise, you've asked your cart to travel, to turn too sharply, and you're going to spin out. So to keep it realistic, it's got to be a tangent. So let's put it, let's try move it away from the edge. It seems to want to snap to the edge. Let's try that. That's pretty good there. Okay. All right. And so that starts there and finishes there. So there's my track. I've laid my track. I still haven't filled in this gap there. That's okay because we need to calculate how much braking distance we need. So we don't know where that flat out section changes to having to hit the brakes. We'll calculate that now. All right. So having done that, we're going to go over to our spreadsheet. And you know what? Here's a blank one that I created earlier. Let's have a quick look at the spreadsheet. It's got a section with assumptions. So these are like our starting parameters and assumptions. And then each segment has got some calculations. So for each section, we've got to calculate the time. And we also want to know the initial and the final velocity. Although for some of these sections where we are moving at a constant speed, we don't need an initial and final velocity. We just need a velocity. So that would be there and there. That's an ideal speed. So anyway, so what we're going to do is we're going to start. See, I've numbered over here. That's the order that we have to think about things in. Actually, before we do that, let's just quickly look at our assumptions for starting. So we're going to assume that our entry point at the end of that straight, we've hit the maximum speed for these cars, which is about 70 kilometres an hour. So 70 divided by 3.6 gives us 19.44 metres per second. Our friction coefficient. Now, we don't do friction in physics anymore, but we do it in engineering. So you physics people who don't do engineering, a friction coefficient tells us how much grip there is between the tyres and the track. The higher the friction coefficient, the more grip. The lower the friction coefficient, the slipperier it is. Now, friction coefficient has no units, it's a ratio, and I won't go into all the physics, but just know that's what it is. So 0.7 is not an unreasonable friction coefficient for a go-kart tyre, so we're going to use that. Acceleration due to gravity, we all know what that is. I've calculated here mu, that's your friction coefficient, times gravity, which is 9.8. That is a formula there. We derived it in class. Maybe on another video I'll show you how we derived that, but basically that's the fastest acceleration or the greatest acceleration we can have with that amount of friction before we start to wheel spin. So that means that's for accelerating forwards, that's for braking, or that's for turning a corner. Because remember, turning a corner, we've got centripetal acceleration. So if we try to get more than 6.86 meters per second deceleration when we're braking, or cornering, trying to get centripetal acceleration, if we try to exceed 6.86 meters per second, we'll spin out or we'll skid, and then we lose control. That's no good. Now, the other acceleration we need to know is, theoretically, if we had a really powerful engine, we could accelerate at 6.8 meters per second, but our karts don't have an engine that powerful. They won't wheel spin. So realistically, the best acceleration we're going to get from our engine, not because of the friction, but because of just the limit of the power in the engine and the power to weight ratio, or the force to weight ratio, Newton's second law, we're going to assume that's going to be 3 meters per second. All right, so that's our starting point. So let's start to put the details from our PowerPoint here into our spreadsheet. So I'm going to start with this corner here. So this corner here, let's see, I need the radius. So 1, 2, 3, 4, 5, 6, 7, 8. I've got a radius of 8 meters. So let's see, 8 meters down here, 8 meters there. And the angle, now I can see already that's 90. That's 90. Oh, you know what? I've stuffed this up a bit, haven't I? Because that's not a complete, it's not a proper circle. Let me just fix it. Let's do that. There we go. That's a proper circle now. I might have to change a few things here. Never mind. I'll do that on the fly. Okay, there we go. So that's a proper circle now. Let me just bring this in a little bit. So that, oh, I can't really do that, can I? Just bring that out a little bit. Oh, I did it again. Need to use the corner like that. So let's see. That's better. That's better. Okay, we'll fix that up there. All right, so we're back to a circle now. So this is a 90 degree. So let's check the radius again. 1, 2, 3, 4, 5, 6, 7, 8. 8 point, oh, what do you reckon? 8.3. So if I go 8.3, 8.3 is the radius of my corner entry. Remember, 1 square is 1 meter. Let's see, and 90 degrees we said. So let's all tab back to there. So distance is, not distance, angle is 90 degrees. Now our spreadsheet then automatically calculates the ideal speed. So the square root of mu, that's our friction coefficient, times gravity, times our radius, is going to give us the ideal speed for that corner. That's the fastest we can go around that corner without slipping. Now, we derived that in class. I'll derive it again on another video maybe. But that's the fastest we can go around that corner. Okay. Now, that's the distance around the corner, and that's 2 pi r, which is the distance around a circle, times our angle divided by 360. So that is what proportion of a circle have we travelled around. So that gives us the distance around the circle. And of course we can use that. We can then using speed and distance, we can calculate time. All right. So why is that useful? Now that we know the ideal speed around the corner, that's got to be our final velocity for this braking segment. So we need to slow down to 7.55 meters per second. Now we know the initial velocity because our initial velocity is just our flat out velocity. That's that one there. And so we know our initial velocity, we know our final velocity, our deceleration, We calculated that before. That's the quickest we can, or the hardest we can brake, or our best braking deceleration before we skid. So that is minus that value there. See, minus C7. And knowing those, again, using kinematics, I'm not going to explain all that, but using kinematics there, we can work out that the stopping distance is 23.41 and the time is 1.73 seconds for that segment. All right, that's important. So that stopping distance there, that's our step number 3. We need to take that distance and update our PowerPoint drawing. So 23.41 is our stopping distance. So let's see, 23.41, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.1. So I guess 24.1 is going to be, oh, I've lost count now. I think that was it there. Let's try again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. What did we need? We needed 23.41, so a little bit more than that. That would be 23. Let me just zoom in a little bit. That would be 23. 23.41 is just going to be, it's not going to let me be too granular. Zooming in so I get a bit more control. Okay, I think that's going to be about 23 point, there we go, that's pretty good, 23.4. Now that means that this little flat out section is only that long. So move across here. So that point there, 23.4 metres, fix that, 23.4 metres from that finish point there, that's where we need to start braking. So this blue section, this flat out section, is really only going to be, you know, let's call that, I don't know, 1.9, about 1.9 metres. So now I can come up here and say that flat out section is only 1.9 metres. So let's see, what have we got? We've got those first 3 segments analysed. We know the distance and the time and the velocity. We know the initial, final velocity, the deceleration, the time and the distance for that segment. Same for all of these ones here. Let's see. Okay, so now we need to analyse our segment 4. Now we already know the initial velocity because the initial velocity just comes from here. It's the same, it's the ideal, so I've got a formula that just takes that. The speed from that corner is our initial velocity for this corner. Now in this corner, we're going to try to accelerate out of the corner. So our final velocity is going to be faster than our initial velocity if we accelerate. So we're going to put some acceleration in there, but in a minute. First, we've got to do some other calculations. So I need the radius and the angle of this corner here. So let's zoom back out again. So our radius, let's count 1, oh, that's about half, isn't it? Let's count from this end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a half. 10 and a half. So let's do that. 10.5. And what's our angle? Is it 90 degrees? It's a little bit more than 90 degrees. Okay, I've put this protractor over here to help us with angles. So if I take this and stick it there, like that, so I guess that goes from 91 through to 183. So what's that? That's 92 degrees. So 92 degrees, Control Z to put it back where it came from. So what did we say, 92 degrees? I think that's what we said, 92 degrees. Okay, so that using that angle and that radius, we can calculate the distance. That's the formula there, 2 pi r times 90 over 360. Or not 90, that's going to be 92 over 360 now. All right, now here's what we need to do here. We need to calculate how fast can we accelerate. Now, our centripetal acceleration, the fastest we'll be going during this circular section here is right at the end of that section if we're accelerating. So that's our centripetal acceleration. Now, we can accelerate better than that, because we can accelerate up to 6.86 meters per second before we skid out. Now we've got 5.4 meters per second of centripetal acceleration. We can add some tangential acceleration, that's sort of like straight line acceleration. We can add some of that. Now, and this final, so let's see what happens if I go 1 there. What does that mean? That means I'm now going 1 meter per second. That's how much my speed is changing, but this is how much my direction is changing. Now, because I've accelerated, that's made my final velocity higher, which is, that's kicked my final total acceleration, my resultant acceleration, higher than 6.86. That's no good. We've got to keep it under 6.86 or we're going to spin out. So we can't accelerate, we can't have a tangential acceleration of 1 meter per second. We've got to be a bit more controlled than that. What if I go half a meter per second? Okay, well, if we do that, well, that's not too bad. We've got 7.03 meters per second. 7.05, that's the one we want. That's the sum of those two, vector sum of those two accelerations. No, it's not just a normal scalar sum, it's a vector sum. Uses Pythagoras. There's the formula. All right, so let's play with this. Let's go 0.3. Oh, actually, that's gone. Now, that's under 6.86. See if we can do better than that. 0.35. Or we can go higher than that, 0.36. We can go higher than that, 0.37. Getting close now, 0.38. What can we get to? We've got to get to, let's go a bit more. Let's try 0.4. Oh, I got that wrong before. We can go faster than that. Let's try again, 0.45. Oh, that's a little bit too fast. See that 0.688 is just too high. So 0.44. That's as good as we're going to get, okay? So that is the hardest that we can accelerate out of that corner while we're still turning before we spin out. So let's assume we're going to do that. Now that tells us, now we know that's our final velocity. See, we came into this part of the corner with a velocity of 7.55 meters per second. We came out with a final velocity of 8.47 meters per second. So our centripetal acceleration got us around the corner, and our tangential acceleration increased our speed from that to that. Again, using some kinematics, that took us a whole 2.11 seconds, automatically calculated by the spreadsheet. We're almost done. All we've got to do now is just put our x and y distances. Remember, this line's sort of sloped, so we need to use Pythagoras to work out the total distance. So let's have a look at that. Back to our spreadsheet. Let's see, our rise and our run. So our rise is, well, I guess that's about, is it 1.3? Let's just say 1.3. So it's this one here. 1.3 is our rise. And our run is, let's see how to count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 23 metres. So that means 23.04. So that rise didn't make much difference at all, did it? Okay, so 23.04. Again, that's our maximum acceleration that we can get out of the karts, not because of friction, but because of just the limitation of the power of the engine. So we've got our final velocity and our final time. So that's our exit velocity, 14.49, and that's the time it took to get around the corner, 7.67 seconds. So let's, actually before I do anything else, I'm going to take a screenshot. So Windows Shift S, I'm going to take a screenshot of that, and I'm going to put my screenshot into Excel like that, just so I've got a record so I know what my calculations were for. Okay, so let's have a look. 7.67, that's compared to the previous example. Ooh, so that line that we did there, even though that's longer, we got around that corner faster because we didn't have to slow down as much for that corner. And let's see, our exit speed on this corner here, that's the first one, was 14.36, and our exit speed here was 14.49. So this is that is a better racing line than that on both counts. One, because it gets around the corner faster, and two, because it has a better exit speed. All right, I'm going to leave it to you now to try and map out what do you think is what's the absolute best racing line you think you could get around that corner. Do that same analysis. So what you're going to do is you're going to take a copy of that, just Control C, take a copy of that, delete the picture there, and then just delete all of these, not those ones here. See the ones with numbers next to them? Or actually not the ones with numbers, all of these ones here that aren't coloured. Okay, so from segment 1 down, just delete that one. See, they're not shaded. Delete those. Delete, 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 delete. Okay, and repopulate those using what you think is the ideal racing line. Okay, see how you go. All right, that was a marathon. That'll do.